Okay, share a screen. Okay, hide this little bar here for me. So, it's supposed to hide. Come on. There we go. This Friday, right? Is that right? Today? No, next Friday. Next Friday would be the last observing event of the year at Brainerd Red Clay Alliance. And then Dave mentioned the holiday party. For anyone stuck at home this Friday night, if you want something to do, otherwise it's advancing.
We're not seeing anything on the screen, Don.
You're not.
At home, I mean.
All right, let me stop the share and try again.
I should say I'm not.
I'm not either.
Okay.
Oh, here we
Thanks
go.
for piping up.
Let me try this again. Slideshow. Beginning. How about now?
Now it's just chunking. It's just like, rolling.
I just see Don Neb has started screen sharing. Double click to enter full screen mode.
Let me grab my other computer so I can look at what's going on. Let's see. I'm going to close this down. Stop share. Going to close all these. Close that. Just close that. Minimize that. So let me open this now. Go back to Zoom. Let me try again. How about now we have? Got it? Okay.
Got it. Got it.
Too many windows open, probably. Leave it till we get John going. Okay. All right. So Friday, November 21, night sky observing, and then the party. If you have nothing to do Friday night, Astronomical League Live is on. This is a almost monthly show from the Astronomical League. And if you remember our club, you're a member of the league. Okay. The league is a collection of about 300 clubs nationwide, 25,000 members. So we are in the Mideast region of the league. So about once a month, the league does a live stream broadcast that goes out over the whole world. Really, it's on the internet. Explore Scientific does the broadcast for us. They're very helpful. Scott Roberts is a great friend of Astronomical League and all amateur astronomers. He does tremendous things. So on Friday about 7 o'clock, if you go to explorescientific.com live, or if you're on Facebook, just search for Astronomical League and you can get a link to the live stream there. So Alan is Canadian astronomer. He's been an amateur astronomer or professional astronomer for many years. Has a couple books out, magazine articles. He contributes to Sky and Telescope regularly. And he's been on Astronomical APOD, Picture of the Day, Universe Today. He's been on all kinds of things. So it'll probably be a good show. And if you notice, I'll be on there for about 5 minutes. So some shameless self-promotion there. So I do a really short night sky review because the VP of the league asked me to help out, so I do. So
What time is that, Tom?
that's at 7 o'clock Eastern Standard Time.
There it is.
Yeah. Okay. So that's Friday night, and night sky lights. So Saturn is ruling the sky. We had an event at the American Helicopter Museum on Saturday night. About half dozen of us were there, and Saturn was like the only thing we saw. It had the clouds rolled in, and just as the event ended, the moon rose and it cleared off, as always happens, it seems. So anyway, Saturn was the highlight of the night. Jupiter will be coming up by mid-December, low in the east. If you ever haven't seen Uranus yet, get your binoculars and you can use the Pleiades as a guide to find Uranus. Neptune, you will need a telescope to see Neptune is near Saturn, and both gas giants, well, all four gas giants at that point will be visible. And Saturn and Neptune and Uranus will be visible all night. New moon is on the 20th, and the next full moon is on the 4th of December. It's called the Rivers Freezing Over Moon. That's from the native Canadian tribes, or the full cold moon, or the full long night moon. Meteor shower is, will that be next week? It's active now. We're lucky the moon is not interfering, so that is usually a pretty good shower. But the best shower of the year, I think, the one I always try to catch is Gemini, and that's the night of December 13th, 14th. That's a good show. I always try to get a look at that. You can get, a meteor every 10 minutes if you're lucky. So that's a good show. So, okay, that's all I have. I'm going to stop the share. I'm going to try to get John's share going, and then we'll get John up here. So I need to minimize this, close that. I'm going to open your file, John. Does it look like it? It's good. Okay, enable content. Yes, trusted. Let me go back to Zoom. Minimize that. Share. There's John. Share. Coming through?
Yep.
Okay, let me hide this. Slideshow. The beginning. You got it, John. Bruce, do you need to introduce John? I don't think so. I don't think it is working. Okay. All right, I'm sure we're working or not.
The man who gets no introduction, that's me.
The man who needs no introduction.
Oh, I'm sorry. That's what it is. I'll remember. Great to see all of you again. Unfortunately, I got called, 2 hours ago? Something like that. So my suit was out being pressed, so here I am. And here we go. Cosmic wrecks. And so we're going to be talking about collisions near and far.
Should we turn this so people can see you, maybe? They can hear you better that way, too. That? Or like that?
That's nice. Thank you. So I've given a number of talks here. You know, I like to set a context. It's just one of the things I do. And so the context is everything. How's that? Kind of narrow it right down. And not really, but almost. The first thing we think about is space. And I don't know how often you guys think about it. Some of the audiences I talk to don't think much about these things at all, but astronomers tend to think about these things. But if we're to believe the theory that seems to, have no strong competitors at the moment, the Big Bang, then almost 14 billion years ago, out of nothing, there was a singularity that has been expanding ever since. And by expanding, I mean space itself. It wasn't like there was a dot in space. This is the part that you can't actually conceive of. There wasn't anything. And so space began, and space has been expanding ever since. And in addition to the fact that we have this unimaginably large area now that we call the universe, within it, it's filled up with stuff. And we won't talk about the one thing, which is dark energy, because we actually don't understand what it is. But about 30% of what's across the universe, literally everywhere across the universe, is matter. And we've now learned that about 1 part out of 6 is the stuff that we actually see and can know about. And the other 5 parts are dark matter, and they exist, we believe, because the way they act with regard to gravity, one of the 4 principal forces, allows us to sort of see where most of the dark matter is and how it acts within the galaxies, between the galaxies, and so on. And so thank goodness for that attractive force of gravity, because without it, all that matter that was spreading out as space spreads out wouldn't communicate with each other. But fortunately, gravity pulls clumps of it together, and we end up with things like suns and the Earth and the periodic table of elements and people. So now think about the more general case than the solar system, and that is all the stars and all the planets and moons and so on, and especially all the galaxies, the largest collection, if you will, of stuff. And everything is moving all the time. Angular momentum is conserved as clouds of gas compact and eventually spin out into disks and form stars in the center and form solar systems and so on. So everything is spinning all the time, and everything is moving, converging. Sometimes if a mass comes by that's greater than the one that you've been attracted to, then it's diverging. But a lot of times things merge, they come together. Sometimes they collide, sometimes they miss each other, and we end up in orbit. But everything is moving all the time. So you have this picture across space of all this matter and everything moving, and there's lots of collisions. And we're going to talk about the different kinds of collisions, starting on the largest scale and then sort of walking back into the nearby scale. And there are things about the collisions to just understand how they happen and what happens and how we know about it and what it means. So we'll start off with a familiar picture here. Probably the most famous image so far from the James Webb, which is what it's been producing. It's been operational for over 3 years now, so there's lots and lots of data out there. But at one point, they had the James Webb stare for a long period of time at a very dark spot in the sky, as opposed to the Hubble, which was, we used to say, a grain of sand at your arm's length. In this case, it's a thumbnail. And so picture that thumbnail multiplied across the sky, all the way around 360 degrees in every direction. And it doesn't surprise you then that if there are 100,000 galaxies in this particular thumbnail, that there are trillions across the universe. It just sort of, these are numbers that are beyond meaning, really. But that's our universe. And we get these beautiful images and we get wonderful measurements of it. And there are literally teams of astronomers all over the world that in many cases are working on what they see in this particular image, especially the very dimmest things that you can find, which typically will have the greatest redshift and the greatest look back time. So everything's receding as the universe expands, except for the fact that really everything isn't receding from everything. There is structure, and the top element in the structure is a galaxy cluster. And there are hundreds to thousands of galaxies bound together by gravity. And so they don't spread apart from each other, they find each other. And you go down to the next level and you have the local groups within the clusters of maybe dozens of galaxies. And so we'll talk about our local group, which has only 2 large galaxies, and we're one of them. And so we'll take a look at that now. So here is kind of a selfie, except we all understand that a selfie is a camera outside of an object looking back at the object. And not only have we not got any cameras outside the Milky Way, we don't have any cameras outside the solar system yet. About the time some of us were, finishing school or maybe even older than that, the US launched these 2 Voyager spacecraft, which have been traveling at tens of thousands of miles per hour outward since then. And so 50 years later, they're maybe halfway out of the matter that's in the solar system. And so it's going to be a long time before we actually get a camera view of our solar system. But this is kind of like it. You go up in orbit and you pan around just like we've all learned to do with our cell phones, and you get that 360-degree view around of our particular place, which is about the halfway out the distance from the center to the edge of our galaxy. And you end up with this view from our point in one of the spiral arms, looking towards the center there. You have the bright bulge in the center. And of course, the dark matter isn't actually something that's matter. It's the fact that there's so much there that it blocks all light from getting through it. And so that's our Milky Way, that's the disk, and that's the bulge in the middle. And here are the two other galaxies that are nearest to us. You've heard of them probably, the Magellanic Clouds, named because Magellan and his crew, I believe in the 16th century, were in the southern hemisphere. And for the first time, after months of traveling around, they came home and were able to describe these two assemblies of stars in the sky that hadn't been seen by us Northern Europeans until that point, and they got their name applied to it. And so we've got the large and the small Magellanic Clouds. Here is our nearest neighbor, the other one of the large galaxies in our local group, Andromeda. You probably are all aware that it's pretty much the only naked eye visible object in the sky that isn't a star. You know, we don't think about that much, especially on an extremely clear night when we see uncountable numbers of stars. But the one thing that's there that isn't in our nearby, within our galaxy, is the galaxy Andromeda. And so we fortunately have this line of sight where Andromeda is tipped. And so we can see the center of it. We can see the spiral arms, and we can see the clumping where the stellar nurseries are in some of those arms, and so on. And this amazing view here with the sawtooth edge is, of course, a mosaic of, it says, 600 Hubble images, each of which was a long time staring at a small region and all knitted together there. So we have this amazing detailed view. There are better views in terms of extension of coverage to the sides and up and down, but this particular assemblage has more detail, more information in every pixel than any of the others do, and it took over 10 years to produce it. And here's our nearby neighbor, only 2.5 million light years away, only 15 million trillion miles away. So when you think of trillions of galaxies and our nearest one is that far away, space is a big place. So I thought I'd divert a little bit. This has nothing to do with collisions, but I kind of liked to dive a little deeper on that particular Hubble image, where they spent a few more years then, after the 10 years of gathering the information, to separate it out into the different color filters, the different bandwidths. And so by doing that, it allows you to sort of time slice. You can choose different wavelengths which correlate to redshifts, which correlate to ages. And so basically you're looking at two of the nearest time slices to us. And those are the ones that still have lots of stellar formation going on. They sort of define the spiral arms and the clumpiness of it. And those are the youngest populations. And then here are a couple more that look further out in time, further back in time, and they're smoothed out a lot with regard to all the material that's coming from the galaxy from those times. So it's an interesting way to look at the structure of the galaxy and what time slice it is that sort of defines that. So now we'll go back to the Milky Way here, across the center there, and you'll note those little tiny boxes are each a galaxy, a small satellite galaxy of the Milky Way. You may be aware that our particular galaxy has got, I think, a couple dozen satellites. And so the little boxes are blown up into the bigger boxes, so you can actually see the shape there on this image. And you note, of course, that being satellites, they're gravitationally bound. They orbit the center of the Milky Way. And I now will show you that the large and small Magellanic clouds there aren't labeled as that because it was thought that they were gravitationally bound. It was thought that they were satellite galaxies, but apparently the most recent research says that they aren't. They're their own entities, and they aren't necessarily bound to the Milky Way. And finally, as far as collisions go, each of those small satellites will at some point sort of deorbit, move in closer and closer to the center of the Milky Way, to the disk, and to the actual center until they actually are subsumed within the Milky Way. And that's a kind of a gentle way of merging different galaxies together, not a very violent collision. So now let's go back to our neighbor for a few minutes and see what we can learn from that. Very familiar view that doesn't just show M31, the Andromeda galaxy, but also shows these other two Messier objects. One quite close into the disk there, and M110 a bit further out. And so what we're able to do now that we have such powerful telescopes and can spend so much time surveying the cosmos is we're able to use a variety of telescopes to look much further out in Andromeda at the rest of the Andromeda ecosystem. This stuff is all gravitationally bound to Andromeda. And so, for example, you have a couple NGC objects up here that are dwarf galaxies that are orbiting. You have these streams of material, and that isn't just artifacts of the image, that's actually streams of stellar material that we believe came about during mergers of other galaxies within the Andromeda galaxy at some time in the past. The giant stellar stream is the largest and most obvious one, kind of a tail of stars and stellar material there. B, C, and D are actually separate streams that may or may not have been from the same merging event. And then there are some on the north side as well. And then finally, there's a whole bunch of what are called dwarf spheroidal galaxies. They're quite small. You'll see the size of them in terms of their mass in a minute here. But there are several of them. Again, they're all orbiting the center of the M31 ecosystem. And down here, you see this object that probably most of you are familiar with, another Messier object, the Triangulum galaxy, which is not, in fact, part of the Andromeda ecosystem. It is the third fairly large galaxy in our local group. And so what, in fact, we've found from all these surveys is that there are 32 dwarf spheroidal galaxies orbiting M31, and there are lots of these streams of stars and dust indicating quite a turbulent past of evolution of the original M31 through the billions of years. And so let's look first at some things about these dwarf spheroidals. Say that 3 times. So,
John,
yeah,
how does that compare to the Milky Way, as far as how many we have?
I will have in a later slide what seems to be the consensus, which is, as you're probably aware, we really don't know.
Right.
But the consensus is we're both about the same size, we now think. We thought fairly recently that Andromeda was quite a bit bigger. We no longer think that. We think we're both in the trillion range in terms of solar masses. So here we have another graphic to show those spheroidals. They're all the red dots there, 32 of them. And just to show you the range of sizes, here's a big one that has 20 million solar masses in it. And yet it's a dwarf spheroidal galaxy, down to one of the smallest ones, which is many orders of magnitude smaller than that, and quite a bit smaller in terms of stellar mass than some of the globular clusters that we're all aware of. So we have a whole range of these spheroidals, and you compare them, and this helps you understand why we call them dwarfs, because of what Don just mentioned there. 1 trillion solar masses compared to only 20 million or 20,000. So the actual galaxies are much, much bigger than that. Couple other facts that I can't dive into the background of, except that they are interesting as to how they relate to these particular dwarf spheroidal galaxies. And that is, you're probably aware, and I guess I mentioned earlier, that as we've surveyed across the universe using gravity and motion due to gravity, we believe there's about 5 times as much dark matter as you take the universe in total. And now we've looked at many, many spheroidals across many galaxies, not just the Andromeda, and we found that they are quite dark matter dominating. In other words, they have 1 to several orders of magnitude more dark matter than they do than a typical galaxy that didn't have dark matter. And so what's interesting is that of these 32 in the Andromeda system, most of them are not as dense. And so it's not something we have an answer to yet. It's just a curiosity. And so let's look again at a couple aspects of these dwarfs. So here they are, and we've purposely colored some of them red because we have this odd distribution where about half of them lie in a plane that's rotating. And so you can picture it better by putting that through there. And there are some that are just sort of spread around, rotating around the center. But there's this particular half of them, 15 or so, that are in this plane generally, and we don't really understand how they got put into one plane. It wasn't expected. We wouldn't have been able to simulate this from first principles, and we don't know what causes that, but we're trying to figure it out. Another part of the distribution, here's another way to view this, with the Milky Way being off to the left and Andromeda being centered there in the center. And it turns out that when you look at them, they're kind of in a plane with most of them on the Milky Way side, which you wouldn't expect at all. You'd expect to have sort of a random distribution. But if you put a plane there through there, it cuts most of them on one side, it leaves very few on the other side, which again is a mystery. And for me, it raises the question, if the ecosystem mass is, or if the ecosystem center of mass is at the center of M31 and the center of all things orbiting M31, and these are mostly distributed on one side, that sounds like something's a little out of kilter. And in fact, that's what the theories are pointing at right now. And so they've asked the question, and they've been working on this for years, to try to explain this distribution of satellites. And so they've looked at these particular objects, M32 right there in close, and M33, the Triangulum galaxy, to try to come up with some explanation for what might have happened in the past to bring this about. And so we're getting closer here to collisions, finally. And so what we have here is what a current theory is of the history of M32, which at this point is a much, much smaller dwarf galaxy, very close in, very compact, and ellipsoidal, as opposed to being a huge spiral, which is what M31 was. But over on the left there, a couple billion years ago, we believe that the progenitor of M32 was maybe not comparable size, but it was much closer in size to what M31 was at the time, which is quite a bit smaller. And through those 2 billion years, the two passed close together until they came to a point a billion years or so ago where they were starting to pull matter from each other. And then they finally came together there in the right. And M31 resulted in this particular shape. And M32 ended up having most of the matter stripped off by the larger galaxy, and as this dwarf elliptical very much close to the plane. So we believe that's what happens. That's the theory. In addition, we think that part of that merger activity pulled material out of one of these two that stretched out into space and created this giant stellar stream away from the disk. And then finally, there's an argument to be made that somehow the merger caused the displacement of M31 within its own ecosystem to some degree, so that it shifted it away from where the spheroidals might have naturally been. Here's yet another theory, way too busy for me to spend a lot of time with, so I'll just point out a couple things. This is the idea that the Triangulum galaxy in that box in the center there started a few billion years ago, and then it swooped down very close to M31 and had a close approach about 2.5 billion years ago. And so what was the shape of M31 and the flatness of the disk at that point actually got stretched and warped, so that finally, after M33 had passed by and gone out to where it is today, quite a bit away from the Andromeda, we now have quite a warped bunch of edges to the Andromeda galaxy. When you look for it, you can see it. It doesn't jump out at you when you look at a typical image of it. In addition to that, we believe that the gravitational pull on M31 by the large M33 as it went by may also be responsible for displacing M31 away from its natural center of gravity and changing the distribution of the dwarfs relative to that. Again, these are just theories. So you're probably aware that galaxy mergers aren't infrequent. And in fact, this is just a small catalog of some that Hubble has taken pictures of, because they're kind of fun to look at, actually. And one of the interesting things is that maybe as much as 10% of all galaxies at this point in time are involved either in a merger now or have been in one recently. Now, on the scale of mergers of galaxies, we're talking billions of years. So we're talking a significant percent of the age of the universe. So it's not like a recent merger, was just shortly ago. And obviously, there's no way that we can take a picture or a video and observe any of this going on, because the time scale is the scale not just of hundreds of millions of years, but of billions. So we've got those as some examples, but I thought a few of them that you might be familiar with kind of show off the things that happen when you have mergers. So here we have the antennae, and we have these wonderful streams of stellar material that get pulled first as the two galaxies approach each other, and then linger out there as they come together in their embrace, if you will, and in this case, create these wonderful tidal tails. And if you look at the center of that, what you have is this wonderful bright blue region, which is very typical of galaxy mergers, where you're actually first passing through each other usually. But when that happens, you have the collection of gas and dust clouds of each of the galaxies that sort of concentrate as they pass through, and you end up with clumps of gas and dust and lots of starburst going on, indicated in the blues there. And some of these, therefore, get named starburst galaxies, as this one is. And here are a couple more that are fairly popular. The mice is fun to look at there with its tails. And the merging spirals over here on the right might be an indication of what's going to happen when Andromeda and the Milky Way get near each other several billion years from now, as the gravitational attraction starts to pull material from each of them toward the other. And then finally, I like this one very well, the space triangle, they call it. And it's because we know from understanding what is actually there in this static view of all the stellar nursery areas, indicating the areas where the galaxy on the left that used to be on the right passed through, going from right to left, and caused a lot of this star birth to take place. And now the galaxy on the left will pull back in, as they all do. They sort of collide, merge, come apart, and come back together until they have completely merged together. And so we've caught this one after the first major pass through, if you will. So now let's take a look at, I said we couldn't actually see a merger take place, and obviously we can't, but what we have here is a nice simulation of our two favorite galaxies, the Milky Way and Andromeda. And down in the lower right-hand corner there, you'll see a counter that tells us that we're now starting up, and there's the Milky Way rotating. We're up to 500 million years from now, about 1 billion years, and you get to see the rest of our local group here in a minute. And so here we have Andromeda down there, the lower left, and Triangulum, and we're all moving relative to each other, but Andromeda and us are converging. And so now we're up to about 3.5 billion years, and we start to pull material from one toward the other. And then we pass through at about 4 billion years. And after that passage, there's some more dynamics until the entire set of galaxies settle in together and arrive at a shape that's typical of what we think is merged spirals, which is an elliptical galaxy. And so they're at about the 5 to 6 billion year point, which is about half the current age of the universe, is what we think is going to be the state of Andromeda and the Milky Way long after Earth is gone, and maybe even longer after the human species is gone. So that's the merger. And so they're frequent, we believe. If you have unequal masses that are merging, like these small satellite galaxies that are first orbiting the center and then move in and eventually merge with the disk, that's a very gentle merger. It's a very slow evolution. But if you have similar mass galaxies and they come together rapidly, like the simulation or like the antennae, or like these two, some 4 to 5 billion years from now, then you get pretty massive changes and evolutions of the galaxies. All right, so now let's move from intergalactic space into just within our own galaxy, and let's talk about collisions of stars. And so what you have when you have a collision of stars is a combination of factors, but one of them has to do with the density of the environment. And so obviously this isn't a selfie of the Milky Way, but it is actually an image of a similar barred spiral galaxy, showing by the star there an arm, which is kind of like where the sun and the Earth and the solar system are, on a spiral arm about halfway out to the edge of the disk of the Milky Way. And so what's our environment here? And what does sparse really mean? You probably are aware our nearest star is about 4 light years away, about 25 trillion miles. That's near. And it turns out that if you look outward in a volume, about 100 light years. So 100 light years, that's 100 times 6 trillion. So that's 600 trillion miles of radius. And the volume contained within that is quite a big bubble. And there are about 10,000 stars we've now counted within that particular neighborhood, which is quite sparse, as you'll see, because we're going to compare it to areas that have dense environments. And so here again is another graphic to show us our Milky Way, with the sun there on the left, partway out one of the spiral arms, with this beautiful bulge in the center, very bright, very dense with stars, and higher and lower than the typical thickness of the disk. And then out beyond that, in the halo region, you have these globular clusters that are orbiting the center of mass of, in this case, the Milky Way or whatever galaxy. And so what are they all about? Well, they're going to be our example of a dense environment for one thing. And so I'll show you one of my favorites first. And that's M13, the Great Cluster in Hercules. And if you've never looked at this through the eyepiece, do it sometime. It's just really nice to see. But at any rate, to compare that to the 10,000 stars in the neighborhood of our sun, what we have here is about 500,000 stars in a volume that's somewhat larger, but not that much larger. So well over an order of magnitude greater in terms of density. And when you imagine what it's like to live on a planet in a star towards the middle of that, and what the sky must look like, it's a very, very different thing than what we have here on Earth. So that's the Great Cluster in Hercules. That's a dense star cluster. And so let's just talk about globular clusters in general. 100,000 to 1,000,000 stars, and this is key. They're all born from the same gas cloud, typically about the same time that the galaxy is forming. And in fact, we believe that as they pull together, as we say, as many as 1,000,000 stars, initially they're competing to become the center of the galaxy, but they don't make it. They are outcompeted by whatever it is that finally causes this huge aggregation of the galaxy. But they're about the same age as the galaxy, which is to say that they're billions of years old, all these stars born about the same time. And so what that means from our understanding of stellar evolution is that many of those stars, the largest ones, the blue hot ones, really burn out very rapidly. That's what we understand very well about the length of time, the lifespan of stars based on their initial mass. And so the massive hot bright stars burned out a long time ago. And so when we look at what's in a globular cluster, and there are a number of them pretty much away from the plane of the Milky Way, we expect to find old stars typically, cooler, smaller, dimmer than some of the ones that were born there with the star at its birth. But I'm going to show you an example here of something that has come to pass that helps explain why we don't always see exactly that today. We'll get to that in a few minutes. So back to the dense star clusters. The globulars are one example, but perhaps the better example is right there in the center of our galaxy, where we have now come to understand at the center of most galaxies is a supermassive black hole. And so you have this massive pull in the center, and the stars that are numerous around it end up orbiting it and eventually being consumed by the black hole. And we're fortunate that we have the instruments like the Keck instrument that doesn't look in the visible band, but it looks in a band where it can actually see through all the stuff between us and the center of our galaxy there. And over time, it plotted these elliptical orbits of a bunch of stars that are moving in and out on their elliptical paths as they go around the black hole before they go into the black hole. And you can just see the different observations there with the dots. So we have this evidence and we can calculate the speed of these. And so we're able to compare that speed to speeds that we are used to understanding, like our sun or our Earth going around the sun. I don't know if you remember, but in science class, I remember being a little bit puzzled to learn that the Earth was moving at 18 miles per second. And I remember hearing that, in middle school probably, and feeling, well, I don't feel anything. That sounds kind of fast. And so it's all relative, as they say, but the Earth's moving at 67,000 miles per hour, faster than any spacecraft has. But you compare that to the stars that are whipping around the supermassive black hole, and they're all going at least a couple million miles per hour. So extremely fast movement as they come around and go back out because they don't necessarily get consumed until they finally are in close enough. And so the example then is for these stars coming from far out of their elliptical path, coming towards the center, and then zooming around. And so they're in a very dense region and they're going at very high speeds, as you've seen. And those are the recipes for stellar collisions. Just like if you have a crowd of people at a train station looking at the board and the time changes and you see a bunch of travelers running through the crowd bumping into each other. Collisions happen when you have a dense field and a high speed. And so what happens, we now understand, and I don't know that we've ever actually imaged this. I've been out looking, if anybody can find this somewhere on the internet, please send me the reference to it. I've read that we have a picture of a stellar collision, but I haven't been able to find one. At any rate, here's what we believe happens. When they slam together, going at a high speed, two stars result, and both of them have less mass. They knock a lot of the mass off of during the collision. And so here's an example from a graphic view from a simulation that was done where you have a 2 solar mass star moving up towards a 3 solar mass star moving down at a relative speed of about 10 million miles an hour there. And so they slam together. And afterwards, there they are, and they're each quite diminished. As a matter of fact, some 71% of the matter of the 2 stars is stripped off and is in the nearby neighborhood, but no longer part of either of the stars. So that's what takes place in a high-speed stellar collision. But if you go out to the region where it's still dense and they're moving at lower speeds, they still hit each other from time to time, and a low-speed crash turns out to be a merger. So you end up with merged stars. Pretty simple. If they're approaching each other at low enough speeds. And so what we have then is the summation of smaller stars that become large stars through this slow speed collision. And then it can happen sequentially to where you get even more massive stars. And so now you see stars that approach the size of some that are born as blue giants. And they may look blue, but they're quite different. They're the sum, literally the sum of several sequential collisions. And so any stellar population towards its birth will have a whole range of sizes of stars, including the blue ones that have the shortest lifetimes, and then the less bright, less hot ones, but still quite hot and large, will have a medium lifetime. And so eventually what you'll end up with, and this happens in the globular clusters, is a dense environment where there's only the less massive stars that are left after billions of years. Except that now what we have found is that there are bluer stars in these populations. And what we now understand is that these are merged stars, smaller stars that have merged together to become larger and hotter stars. And so they have a special name. They're called blue stragglers. And so when we look for them, we can look in these globular clusters, and there's a number of them, especially towards the upper left there, that we believe to be blue stragglers that have a collisional origin rather than actually being true young, bright blue stars. So in summary, a dense environment is required for stellar collisions. We have 2 examples of that in the galaxies, the globular clusters in the center, and high-speed collisions yield these massive stripping events where the stars change in size greatly and have most of their material stripped away. And for the low-speed collision, we can end up with young-seeming massive stars, but they're really not young. They're old stars that have merged together, and they're called blue stragglers. All right, so now we'll come back within the solar system and come down to from the beginning of the solar system to today. And so we'll just start off with that familiar view. There are many versions of this. You've all got your favorite probably. I like this one in that it kind of highlights the fact that we don't just have the asteroid belt that we were all taught about in school. We've got the other asteroid belt out there beyond the 8 planets at the Kuiper Belt, where Pluto lives for a lot of the time. And so one factor that I did want to note here was kind of surprising when I learned about this recently, and that was that from the earliest time, when of course there was much more in the way of numerous smaller objects, planetesimals, planetary embryos, and so on in the solar system, there was a whole lot more matter that was in those 2 belts than there is today. But through a process of the radiative effects of pushing matter out from the sun, but mostly, I believe, from the migration of the gas giants and a lot of collisions, a lot of that matter, as a matter of fact, it's believed that 99.9% of that matter was actually taken out of the solar system at the time. And so what I take from this is just to kind of imagine if the asteroid belt had 1,000 times as much in the way of mass in it. And we know that it's the collision of those asteroids that many times creates these near-Earth asteroids. They sort of deorbit. It would be a much more dangerous place today if most of that material hadn't been removed early in the life of the solar system. Now let's look at some of the other early solar system events. So here we have the 4 terrestrial planets. And the yellow and the orange there is the core part, and the tan part is the mantle. And at a glance, you can kind of see that the proportion of mantle to core is much higher for Mercury than for the other 3. And we believe that's because a relatively large object, about the 1/6 the size of Mercury, hit it early in its life and caused it to eject about 80% of its mantle. The second one is a look at Mars, and a look at the elevations on Mars gives us a clue to something that was an impact. And of course, we see the pockmarked evidence of impacts on all the planets, all the crusty planets, if you will. But in this case, with the Mars orbiters that we've had that have created these wonderful maps, this particular map shows us color-coded the elevations of the surface of Mars, where the equator runs across the center and it goes all the way around the planet there. And so it just jumps out how much lower in elevation the northern hemisphere is than the southern hemisphere. And a lot of that, we believe, was from one particular impact that's called the Utopia Basin there, where you see this extremely large impact basin from what's believed to be the largest impact ever in the solar system that removed a lot of the material, not just there but from other parts of the northern hemisphere. So that's quite an interesting collision there that took place. And you've probably heard the leading theory for where the moon came from. It was believed that in that first 100 million years or so of our 4.6 billion year life, that the embryonic Earth, not yet fully formed, was impacted by something about the size of Mars, and that the material that then streamed out and mixed from the 2 bodies ended up doing a couple things. One was when they finally came back to being round in shape, being orbs, a lot of the mantle had mixed the material of the 2. And since we visited the moon, we've now learned that the material in the mantle of the moon is very similar to the Earth's, and that would explain it. And also the moon lacks an iron core that it might very well have lost during that early collision. So now finally we get to
John,
the,
can I ask a question?
yes,
One thing I've always had a little struggle with is because if you look at Mercury and the size of the core and the theory that's put out that it actually was a collision, so a lot of its mantle was lost, and yet the same thing didn't happen to the Earth. You know, so even though we say there was a collision that formed the moon, and yet we still have a very large mantle compared to the core. So is it really I don't know what the answer is, maybe you have a better theory. Is it the angle at which the colliding body came in that made the difference?
Um, you and I aren't planetary scientists. I imagine they have a range of theories and a favorite, but I think at least two of the factors have to do with how far past the aggregate birth of the planets this took and how hot and formed they were at the time when the collision took place, and also the relative size of the impactor. Now, if their theory that it was 1/6 the size of Mercury is true, then that's a smaller fraction of the target than in the case of the Mars-sized body and Earth. But it could be that it happened at quite a different time. I don't know. I don't know. I would guess that it has something to do with the age of the planet when the impact took place.
Interesting point. Thank you.
So here we have the 8 planets and an interesting graphic to indicate something that you kind of would expect, which is because the original gas cloud that formed the solar system was rotating like everything does. And eventually that rotation caused it to spread out into a disk. And that disk had everything rotating the same way as the sun when it was formed is now rotating. And the planets, as they go around, are going around. And the planets in general are rotating in that same direction. But indeed, you look at the rotational axis here for Uranus, and there it is lying on its side instead of being straight up and down, which is relatively what you would expect it to be. And so the guess there is probably an obvious one, that early in its life, something really big knocked it sideways. Now, knocking Mercury or Earth sideways is one thing, but this is a gas giant. So I'm not exactly sure what knocking a gas giant sideways is, but that's the theory, or else that there were several events that hit it at this particular angle while it was in its embryonic form. So those were long ago. Now we'll come up to date and we'll talk about some recent collisions. And of course, you can tell by this little picture, the first one I'm going to mention is the one that took place on the north side of the Yucatan Peninsula with an asteroid about the size of Mount Everest, hitting 66 million years ago, we believe, and causing so much matter to be put into the atmosphere that the Earth was basically cold without any solar energy getting through to the surface for maybe decades. And so 85% of life died off, plants and animals. And most important, and mostly, this was a species that had been around much, much longer than human beings have. I believe tens of millions of years the dinosaurs had been around and they went extinct. And thank goodness, because it opened up some ecological niches that led to the evolution of humans. And so it could be that had it not been for something like this, we might not be here. The dinosaurs might still rule the earth, and we might never have been able to get into the competition. And so the most recent one is this particular one observed from a truck going down a highway as you see this bolide exploding. Now that's the day after Valentine's Day 12 years ago at 9:20 in the morning. And so all these people driving their cars and looking down the highways and so on saw this event take place. And it turns out that fortunately, since it was in central Russia, it was far away from the population center, and it was also 14 miles in the air. And so it's roughly 25 to 30 miles away from this city of Chelyabinsk, which is quite a large city. And so at 25 to 30 miles with the acoustic wave, the pressure wave, the concussion, and the sound all arriving at the speed of sound a mile every 5 seconds, it took 2.5 or 3 minutes before they actually heard what they saw. So they all got their cell phones out and called their friends. Everybody went to the window, and this is what happened. And so the main result you hear there, and that's breaking glass and automatic cameras being knocked off their moorings and car alarms going off and so on. But all those people that wanted to get a better look went to the windows. And so there were, well over 1,000 people injured by flying glass. No fatalities, only because this roughly half megaton explosion took place 25 to 30 miles away. But had it been right near any population center, there would have been lots and lots of fatalities. So that can happen still. And this particular size asteroid, we think, comes about once a century. The last one that was this size was the Tunguska in eastern Siberia, which also had very few people within literally hundreds of miles. And so there was no record of any fatalities from that. So it can happen, and it does happen. And that's the worst of the collisions in terms of human disaster. So in summary, early in the life of the solar system, there were giant collisions, a variety of results. There was roughly 99.9% of the material in the asteroid belts removed during the formation. The massive impacts eventually made way for humans with the the Chicxulub there. And finally, we can be thankful that no population center in modern times has been impacted by an asteroid. That's it. Thank you. Any questions? Yes, sir.
Why did it explode 40 miles up in the air rather than coming up on the ground higher?
Bolides, which are exploding asteroids in the atmosphere, are common. As a matter of fact, if you put in bolide map into your browser, you'll get a map of the 100 of them in the last 5 years or something, and where they occurred and what size they were around the world. Is that correct? Does everybody understand them that way? And so, I mean, that's the name of them. It's a matter of heating. If they're small grains, little rocks, they probably burn up with a nice shooting star effect. But if they get very, very hot and then come down through thicker and thicker atmosphere, eventually at some point they just break. Yeah, and explode. Like an air bursting nuclear device. Yes, sir.
That's sufficient movement's going to be left in the ground.
What's that?
But if there's sufficient mass,
Yeah, they found a number of pieces of it too. I mean, I'd love to get a full hour talk about Chelyabinsk sometime. They found pieces in the lake and, quite a lot of pieces. Yeah.
Have you ever thought or imagined in your mind what the heavy bombardment of the Earth used to be like?
No, I mean, today, if we were on the moon today all the time, we'd understand what bombardment is because it's very common for meteors to hit the surface there. Yeah. Thank goodness. I mean, this is the perfect place to be. We're trying to screw it up, but not yet completely. Anybody else? Anybody online? Thank you.
And John, once again, thank you for stepping in on such short notice and delivering a great talk with our other speaker unfortunately had health problems. And
Well,
really-
I was supposed to be here in February. I just happened to be ready enough that it was pretty easy to pull it together.
but we owe you dinner. So, anyway, don't forget, next month is gonna be our holiday dinner. Bruce, if you wouldn't mind giving us just a little primer on what what we have coming up after that.
Yeah, so our speaker in January, I think I mentioned this maybe last month or so, I mean, I don't want to misquote, as been said. Speaker in January is from Drexel University, and her name. Sorry, we rescheduled this from much earlier because she was traveling. Her name is Dr. Naoko Karahashi. She's from the Department of Physics at Drexel. She's a neutrino astronomer, and she's going to give a talk on advances in neutrino astronomy and a new view of the Milky Way galaxy from the Ice Cube Observatory that's in Antarctica. So that's why we had to reschedule in Antarctica. So she's published a lot in this field or as part of large groups, and she'll probably be here in person.
It'll be interesting because we had speak with us many years ago, Dave Goldberg was down there, who also was down there floating balloons and research in the ice stations down there. So that'll be a great follow-up talk. We'll have some great questions for her too, I'm sure.
And then in February, tonight's speaker.
Hopefully,
Yeah.
we'll be healthy and
Yeah.
ready to go.
Yeah.
And so anyway, we look forward to seeing as many of you as possible with friends, family, spouses, and whatever else at Victory Brewing Company in Downingtown next month on the 9th. Hope to see you all there.
One quick thing,
Yes.
the KP tonight is over 7, and I just had a neighbor
Yes.
that the northern lights are out
Now,
now,
get out there.
so take it home, your way home.
Grab a cookie and go.
The KP index, which is actually disturbance, horizontal disturbance of the earth-magnetic field caused by the sun. So I see that. So it's a measure of sort of really high, it's above 5, you have some chance, 7, you have here.
Okay.
It's always something new.
It's not the right guys. That guy, he's the one.
No, well, right now, reservoir.
I was fair here, some of the, and I never system is still 20 minutes every time, so that's so really nice to hear.
I also know what that's the one. Where was it? So I was up to download the software.
Oh, yeah.
Yeah, they could have.
A lot. The changes you have a cell phone, but you can better lock it on partner systems. You can still get sometimes you get a split of it.
Yeah, I think a lot, and like.
It happens quite a bit. You have to pick one or the other, just, I found that to be, so when I used my phone, it gave me a devil.
Yeah.
But
My wife and I went
like an
to
iPhone,
some
or it's one or two of the cameras.
Disco area, which is supposed to be one of the most premier areas for seeing aurors. We spent 5 nights, it was February 20 to 30. We were 4 here. And we had items every night, they were pretty good, and then the last night.
Even during the day, you have one inch above, one inch below.
Curtain,
You have to figure out.
ground,
Which one exactly.
it was like, I was like, oh my God.
The ability to do that.
Every so often, you get something in your life, so we don't remember.
Yeah, I have to go online to your particular
So
phone.
go there, get a change.
How to trick your phone.
Gotta like
Load, you know, that is. But you know, makes it up. Thank you. Take down. I took.
Yep. Thanks.